This is Ewan Crawford. We both work at Codeplay in sunny Edinburgh. If you love castles and compilers, you should definitely look us up. Today's talk, as mentioned, is going to be about RenderScript, which is Google's language for heterogeneous compute and acceleration. We at Codeplay built a debugger for RenderScript based on LLDB, and that's primarily what this talk is about, how we did so, and some of the things we found about LLDB that are really powerful, some of the really powerful mechanisms we used, as well as some of the challenges we faced with this heterogeneous language. So the talk's about 30 minutes. We have about 5 minutes at the end for questions. 5 minutes again to your questions. First of all, though, we're going to give a little brief introduction to RenderScript, just so we're aware of what it is, what it does. Then Ewan's going to talk about the RenderScript runtime. This is a language based on an actual managed runtime that can do scheduling, etc. And then we're going to get on to the real nitty-gritty of LLDB itself, how we added support for this runtime to LLDB, talk about some of the really powerful hook mechanisms that LLDB exposes to the programmer, and then finally, I'm going to discuss some of the challenges with the LLDB JIT that we really hope we've solved. So I'm going to hand you over to myself to talk about RenderScript, just briefly. So let's talk about RenderScript. As mentioned, it's Android's heterogeneous compute API. And as with many of these languages that are designed to run on accelerated targets, the primary method of exposing this to the programmer is through a kernel. RenderScript itself uses an extended form of C99 to define these kernels, and they live in RenderScript files which have the suffix rs. Now, RenderScript itself, because it's an Android-based language, its really primary mechanism, in addition to performance, is portability. So as with everything in the Android ecosystem, the programmer should be able to define their source once, compile it once, ship it off to the App Store, and expect it to be able to run on any device, whether that be a handset or a dev board or even a standard desktop workstation with an Android distribution on it. So to that end, we actually have to have two compilers. So we have Slang on the front end and BCC on the back end. Now, Slang takes the RenderScript kernels and emits a portable form of IR based on some assumptions of ARM v7 architecture. We'll go into a little bit of detail later on about why that might be a problem. And then that's stored in an APK, which is Android's package manager, and that's shipped onto the device. Once it's on the device and the user launches their app, when they want to actually do some accelerated code, BCC, which is the back-end compiler, it's a small stub compiler based on LLVM, that runs on the device, and it performs some RS-specific fix-ups, which I'll go into in a second. Now, some of you might be asking, why have we got Slang and BCC? Why are we reinventing the wheel when we have Clang and LLC, which do the job very well? Well, the primary reason for that is that we have this reflected API we're talking about here. So we might have a RenderScript, script.rs, which defines some user data. And the Java application that launches that RenderScript will actually get access to all of the objects defined in that. So what are those objects? Well, RenderScript's primary data object is called an allocation, and that's kind of an analogous to an OpenCL buffer. It exists in 3 dimensions, x, y, and z, which are then scheduled onto the GPU or the DSP accelerator, or even the CPU as it runs. And then, as I mentioned, on the back end, we've got the BCC compiler, which is based on LLVM, taking the portable form of IR from the bitcode, shipped in the app. That is then compiled to a shared object, native code, and it's given the name librs.whatever my script name is called, .shared object. And then we have this fork and exec where the RenderScript runtime actually executes the compiler out of process to avoid crashes, and then DL opens that native shared object at runtime so we can get access to all the niceties of RenderScript. So as I mentioned, allocations, they're the primary method of computation, well, storing user data. They can contain something as simple as a char or a uchar4, which is one of the extensions to C99 that RenderScript offers. We've got all these nice vectors available and operations on them. And it's organized in 3 dimensions. So that's kind of like a basic introduction to RenderScript. And Ewan's actually going to talk now about the runtime that runs on the Android device, and then we'll pick up with LLDB.
Cheers, Luke. So I'm going to talk to you about how RenderScript works underneath the hood, and then how we've extended the LLDB to take advantage of these implementation details in order to provide a really nice debugging experience. So I'm just going to start off with a quick overview of some of the libraries that make up RenderScript, nothing too in-depth. Got librs.so, and this is just the majority of the implementation for the host side. So that's things like setting up your RenderScript context and environment. And then just to the side of that, there's librsdriver.so, and that's a kind of interface between the host code and then the script or kernel side code on the actual accelerator you're targeting. librs CPURef is the default fallback implementation of RenderScript in C. So if you wanted to implement RenderScript for your hardware, you'd need to create your own library implementing the same API as defined here. But for the minute, for our debugger, we're really interested in librs CPURef because we only support debugging CPU RenderScript right now. Oh, that's across MIPS, x86, ARM, 32, and 64-bit targets. So the vast range of consumer Android devices. And then finally, we've got compiled script share libraries, and these are when you've got your script bitcode, it passes into the BCC JIT, and it creates your shared library at runtime. A bit more detail on what BCC does behind the scenes. And one of these things is when you've got a kernel, say it's called myKernel, BCC will create a function called myKernel.expand that controls how this kernel is invoked in parallel at runtime, so all the scheduling information you might be interested in. For our debugger, though, the real piece of information that's vitally important is the current thread ID. So in RenderScript, you can execute in 3 different dimensions, X, Y, and Z. So the way we access that is through 3 different variables in the .expand. We've got rsIndex, which is a local variable, and then we've got Y and Z, which come from a pointer to this struct that's passed in. And this struct contains tons of really useful information about how the scheduling is done, like what chunks are being divided up thread-wise, and just the total scope of all the threads. But really, this is what we're interested in, the current thread ID. So initially, this was like, oh, brilliant, all this information is already here. We can just go ahead and grab it. But then we ran into a bit of a problem. And that's all because it's implemented in IR in the back end. We've got no dwarf debug information for it. So we couldn't really access this conveniently. But fortunately, at Codeplay, we've got lots of very smart compiler engineers, so we managed to rope one of them into extending BCC for us, so that automatically adds that dwarf debug information. The way it does this is that we've spoofed a source file name called generated.rs, where this .expand function lives, and I've given it a dwarf debug language, Google RenderScript. So this is different from the default C99 source language for pretty important reasons that we'll come on to later when we talk about JIT. But for now, suffice to say that although Google RenderScript isn't part of the Dwarf 5 upcoming standard, it is planning on being in future releases. And so right for now, it's classed as a language extension, so it uses a reserved identifier space. And we've put that upstream in LLVM, so you can use that right now if you want. So that's a bit about how RenderScript works, and I'll go on now to talk about the other side of the coin, and that's LLDB and how we've extended that. Before I get into the nitty-gritty details, though, let's talk about LLDB's architecture, and that's largely based on plugins. Plugins are just modular pieces of functionality that are dynamically loaded at runtime. So this is easiest explained just through some examples. So say you're debugging ARM code, you'll use the ARM API plugin. If that's coming from an ELF file, you'll use the ELF parsing plugin, and if that's on Android, you use the Android platform plugin. So this is really nice because it means you don't have to cross-compile or recompile LLDB for every debugging situation you're in. LLDB works out from the environment exactly what functionality you need. Well, what kind of plugin is RenderScript? Well, it's a language runtime. This is slightly different from a language plugin because RenderScript is essentially C99. So we can already use all that front-end Clang and C stuff we've got in LLDB. And instead, we use it as a language runtime in this directory here inside the source tree. But how does LLDB work out that we need to invoke this plugin, that this is the functionality you need? Well, that's just by running a RenderScript command. And inside that command, we'll access the plugin manager, which controls all the plugins in LLDB. And just as when you load up LLDB for the first time, it registers them all. And then at runtime, it automatically creates an instance of the exact plugin you need. And our commands just specifically invoke the RenderScript plugin by requesting the RenderScript language runtime. And that'll create a singleton instance of our class. Just see here, some of the commands. They're all prefixed with the words language runtime, and then an object and then an action. So that's very much in line with the structured way LLDB commands work, where you have an object and then an action to perform on it, like process attach or modules list. And it's the same with RenderScript, where you can have, say, an allocation, and then you want to dump it or list them and things like that. To find out more about the commands, you just prefix them with help, and that's the same with any other command in LLDB. I'm not going to talk too much more about what all individual commands do, but there's one in particular I'd like to talk more about, and that's the kernel breakpoint command. So that's just for putting on a breakpoint on a kernel, which is the same as just a normal function breakpoint you might have when you're debugging a regular program. And in fact, because we're debugging CPU RenderScript, the vanilla LLDB breakpoint command will work. I can find the symbol fine, it can place the breakpoint, it'll get hit, that's all no bother. But there's some very good reasons why you should use our kernel breakpoint command and why we went to all the effort of implementing it. First of all, that it invokes our plugin, as I just mentioned, but also we can narrow down the scope of where we're searching for that breakpoint to get resolved. Because right now, we know exactly what RenderScript modules the process is loaded, so we can narrow down our search to just look in exactly these shared libraries in order to find the matching symbol. So this reduces the chances of, say, putting the breakpoint on a conflicting symbol that's there by accident. Additionally, if, say, you don't compile your application with debug info and we can't find anywhere to put the breakpoint, we can fall back to that .expand function that's created by BCC, put the breakpoint there as an approximation. So that's quite a nice fallback mechanism. And the way we do that is just by overriding the breakpoint resolver class in LLDB. A couple other nice things that come from having our own command is just flexibility in the future. We want to support other accelerator targets. And we can also add our own command line flags to our breakpoint command, such as a specific thread ID the user might want to break on. It's kind of like a conditional breakpoint. Moving on to something a bit different, and that's the modules.load API in LLDB. So this is defined in quite a few places, but we implement it again in RenderScript. And this is because we inherit from the language runtime base class, and that defines this as a virtual method, which we want to override, because we get alerted of when modules get loaded by the process, thanks to the dynamic loader plugin in LLDB. This is really important because BCC, that backend JIT, takes the script bitcode and creates that shared library, loads it at runtime, and we really need to be aware of when this happens so we can grab a copy of it for putting breakpoints in it and just accessing other details. The other time this function is actually called is in our constructor, where we pass in just the complete list of all the shared libraries that our process is using. So that way, via this modules list parameter, we've passed in all the complete view of shared libraries that the process has. But what are we actually doing in here? Why is it so important? Well, we're just looking for RenderScript libraries. And that's mostly by name. We're looking for librs, librs driver, librs CPU ref. And when we see them, we can just cache a local copy of them to do custom stuff on later. But there's also a bonus of having this API. And that's that whenever you see these shared libraries have loaded, you can trigger essentially an action on them. So say we see librs driver is just loaded, we can go ahead and put some hooks in that, which we'll talk about in the next section. Or say we see librs is loaded, we've got a loop that's spinning inside the process that waits for our debugger to attach. When we see librs has just been loaded, we can go in there and break out of that loop essentially and continue on with the process. And if we didn't implement this in modules did load, we might have to add a specific user command for it, and that would just kind of ruin the user experience a wee bit, so it wouldn't be as nice. One final problem with this is that although you can search for most of the RenderScript libraries by name, those compiled shared objects from BCC, the scripts, their name is librs your script name.so. So we can't exactly search for the complete name because it might change. So instead, what we do is we search for a custom symbol that's put there by BCC, and that's .rsinfo. And this encodes some custom RenderScript information. So as well as using this to detect RenderScript libraries, we can also use it to parse out that information that's encoded there, because by scraping it, we can display some pretty relevant information to the user that they'd want to know about. The way we do this is pretty easy. We just know the name, we know it's going to be in the data section, so we can just grab a pointer to the internal symbol object in LLDB, grab its address in the file, its size, and then just put it into a buffer so we can parse it. A quite interesting alternative way you can get its address, a symbol's address, is the process load address. And if this is a symbol to say a global variable, by accessing the process load address, you can modify the variable through that. But that's not particularly relevant in this situation, but it's a useful technique to know. So once we've got this buffer, we can just do our custom parsing on it. We can fish out all the kernels inside this script shared object. You can have more than one kernel in the script. That's pretty relevant to display to the user what kernels they can put breakpoints on, and also just other resources like global variables that the user might want to know about. So the last thing I'm going to talk to you about is hooks and what we've used them for in our plugin. So just to clarify what a hook is just an internal breakpoint with a callback handler. So an internal breakpoint is a breakpoint that instead of trapping back to the user is consumed internally by LLDB. And the way that it's consumed is by a callback handler, which is just a static function that can perform any sort of functionality you want. And because that callback is so versatile, hooks are a really pervasive debugging technique. The way you set that callback in LLDB is via this API here. And something to notice in particular is the baton parameter. This is just a pointer to some sort of persistent data, so it could be on the heap or just static data. We can pass a pointer into it, so every time the callback is hit, we can access that pointer to retain some sort of state that we can compare what the current process is like against something we're expecting it to be. We've used this to quite interesting effect to create something called software watch points. To kind of expand this idea a bit with your traditional hardware watch point, say you put it on a variable x. Every time x changes, you're made aware of it. But you might really be only interested in when x is one particular value. But you still have to hit the watch point every single time before you get there, which can be a bit frustrating. Instead, what we do inside our callback is we just have the expected value we want inside the baton, and then we compare the current process state against it, and only if it matches, then break back to the user. Expanding this idea to a RenderScript context, what we have is a kernel breakpoint with a specific thread ID that we want to break on. It's only for an invocation of that specific coordinate. So the user specifies this in the command line flag with the x, y, z components. We bundle that all up into a struct, allocate it on the heap, and pass in the pointer as a baton. Then inside our callback, we've put the hook just on that kernel we want to break on. Inside the callback, we compare the current process state against the baton. If they match, brilliant, break back to the user. Otherwise, it's no bother. Just automatically continue the process and wait till the next time the breakpoint's hit. The way we check the current state of the process is because we've hit a kernel breakpoint, we can just walk the stack looking for the .expand function. And once we see it, because we went to all that effort of adding debug info to BCC, we can just easily check those three variables, compare them against the baton really simply, and then break back to the user if they match. So that's quite a nice bit of functionality thanks to hooks. Another pretty different way we've used hooks is to read function parameters from the RenderScript driver. To give you a bit of background on why this is important, although you can compile applications with debug info, it's pretty uncommon that your runtime is going to have debug info attached to it. It's probably just going to have normal symbols if you haven't stripped it. So it takes a bit more effort in order to get the information you really need out of the runtime. Because of this, what we do is we put breakpoints on functions with parameters we want to know information about. In this example, this is for when allocations get created. It's in librs driver. So every time an allocation gets spawned or created, we're made aware of it by hooking this. And it's really important that we know about allocations, because that's where the user's data lives. And it's pretty common that the user might have an unexpected value in their data, and they need to debug it. So we really need to tell the user all the information possible we can about what's going on inside this allocation. So we put a hook on this, but it's not quite that simple because there's no debug info. So what we actually put a hook on is this massive symbol that's so big I can't even fit it on the slide. But fortunately, that gets resolved, no bother. What we do inside the callback is check these parameters for the context and the allocation. Again, we've not got any debug info, so this is a bit more involved than it would be in an ideal world. What we have to do is read stuff from the register, read data from registers and from the stack, depending on the ABI of the target we're debugging. And because that's quite a few architectures, we've got quite a few switch cases inside our callback for each one of these architectures. But we can absolutely rely on that ABI to be 100% correct for the calling convention and read these values from a stack of registers, no bother at all. So we can get an allocation pointer and a context pointer fine. The only problem is that although we have a pointer to this allocation class, it's a big C++ class, and what we're really interested in is some data that's in a HAL table right at the bottom of it. So it's a bit more effort to get any real constructive details about this allocation, because we want to tell the user how big the allocation is, what type it is, what the element at offset x is, not just whether it is some allocation that's been created, because that's not that helpful. So how do we find out these details? Well, we could put more hooks inside the runtime, but there just wasn't any more functions in there that we could put a hook on, so that was a bit of a problem. We couldn't go ahead and add some more because that would break backwards compatibility, so we encountered a pretty big challenge here. In order to reveal the solution of how we solve this, I'll pass you back to Luke.
Thanks, Ewan. Thanks. So the problem statement really is how do we find out something that's dynamically generated in a JIT in essentially something that's fixed, the binary emitted by the Java compiler. What we do is, some would say is a hack, others potentially Lisp programmers would say it's beautiful. We JIT the allocation details, which is essentially meaning that we do eval at runtime inside our debugger. So just a little bit of the background on the LLDB JIT. So I think most people are familiar with entering expressions, basic expressions into debuggers, doing simple arithmetic, calling functions with parameters. It's done in lots of different ways. I think older versions of GDB used to actually call out to the system compiler and then copy a binary image into the current processor's address space. LLDB, being an LLVM project, does things slightly differently. And we actually get access to all of Clang. So we can actually call basic user expressions or even advanced user expressions in any language that Clang supports, which these days is quite a few. And because of the LLVM backend, we can target this to pretty much any architecture that exists in LLVM. We're familiar with the basic entry of expressions into an interactive debugger, but what we're really interested in when we're building the debugger is the API to do this automatically. So say we have an instance of a language runtime. In this case, we've got our RenderScript plugin, and we want to call a simple function, add 2 ints. Let's just assume that it takes 2 integers as its argument, and we want to find out whether that actually equals 9 or whether we have some serious bug in our arithmetic. So what we do is we create a value object shared pointer, which is one of the LLDB classes, to store the result in. An execution context is really important to LLDB here, and that contains everything we need to know about the current thread, the target status, registers, stack frames for all of those threads. And then we can optionally create some, we can set, for example, one of the target languages supported by the Clang front end. LLDB, also has an expression parser for Go, but we're dealing exclusively with Clang here, so that's kind of beyond the scope of this talk. And then finally, we ship it off to the evaluate expression method, which exists on a target object, which is in process/target.cpp, I think. We pass it a C string of our actual expression, add 2 ints, 4 and 5. We give it the current frame. That could be manually selected. You get a thread list in LLDB, and you could give it that. Or you can just get the current one if you're single-threaded. And then we need to pass in a reference to the expression result. And the options parameter is also optional. And then we can look into the expression result and get its value. So that's fine. That's great. But we've still got this problem about allocations and their object types. So as I mentioned very early, we actually can allow in RenderScript essentially any user data in an allocation. So we need to find a way to do that. And this is what we do. So we build up expressions as C strings. Essentially, it's kind of a form of primitive eval where we have hooks in the runtime that we want to call with parameters that we define, and that way we can pretty print some of these things. The other side of the expression evaluation is interactive kernel-side jitting. Now, like I said, we need to be able to allow the user to call functions. And we've got a bunch of functions that are defined by RenderScript as being the public API. It's fairly limited for two reasons. One is handheld devices are a very common attack vector, so we need to whitelist essentially some good functions. Second is a problem that my colleague Victor was explaining some solutions to this morning, is that when we're on an accelerator, we might be in a different address space. So all these functions are defined in IR and compiled by the driver at runtime. Unfortunately, as I mentioned earlier, we've got a problem with the portability of this. We don't know what target we're going to be hitting at the back end, and we have this assumption of ARMv7 at the front end to be portable for the developer. Unfortunately, there's no way for us to change this. We've got this current dwarf expression parser Clang object, which finds out when we give it an expression, it looks into the dwarf symbols and finds out every parameter that we want, and it gets its declaration for the Clang asked from the dwarf. Because we have this front end that says it's ARM, we get some differences. So LLVM RSCC, or slang, the front end compiler, generates ARM IR. And then we've got x86, this terrible architecture with 4 general purpose registers on 32-bit. So everything is passed in the stack. So when we try to build this expression for Clang, the IR that it generates actually doesn't match, and we get a nasty seg fault. So the allocations, the primary data unit of RenderScript, 32 bytes. Therefore, we got a 256-bit value for the allocation. And because x86 requires all values to be passed in memory when they're larger than the largest register pair, they need to be returned on the stack. ARMv7 doesn't have this limitation. So essentially what we need to do is insert what's equivalent to a this pointer or a struct return pointer as the first argument. So this is what we were getting. We got a long 4, which is actually 256 bits, because RenderScript, all longs are 64-bit. It takes 3 parameters and returns 1. What we actually need is this. So this long retval was actually getting whatever value the user was giving in as their first argument, rather than the hidden structure return pointer. So we needed to make some modifications to the JIT. And as that previous diagram showed, there's no way for us to get this information, and the primary place to do that is from the RenderScript runtime. So we needed to find a way to get LLDB to learn some options. So as mentioned earlier, the AT language field from the dwarf was very important. And we needed to find a way to query the language runtime plugin for these options. So that could be compiler options and data layout, or others. So what we've done is basically built into the infrastructure of LLDB's JIT front end to allow us to query the current stack frame language from the dwarf, call back into the language runtime, ask for compiler options, and then perform our own LLVM IR passes to insert these missing pointers where needed. And of course, this is going to be really important for when we actually go on to accelerated targets. So we had this before, where we have this basic, this is obviously very simplified, this basic flow from the Clang expression parse constructor to copying the function into the target. And now we have this. So we can get the frame language, get the language runtime, get some overridden options that are then passed to the JIT compiler. And then when Clang is emitted its module of IR, we can do the same again and get some extra LLVM module passes that we can then run over that IR and fix up. So I think we're running out of time. I would like to cover what's next, but I think we should just skip ahead to the questions, if anyone has any. Okay. So some of the next things we could do are, fairly obvious things. Hardware accelerated RenderScript is going to be a real challenge. And I think we're really going to need some of these powerful APIs that we've discussed for hooking back into things from LLDB and its kind of runtime flexibility that a lot of other projects don't have. So that's something that we've found really powerful. There's some other interesting parts of RenderScript, such as script groups, reduction kernels, and single source debugging, which combine RenderScript kernels in interesting ways and schedule them in interesting ways. We're going to have to find some more packaged ways to get back into the runtime. And then, of course, user interface niceties like auto-loading the runtime when we detect that dwarf language in any frame. So, yeah, I think we can have 5 minutes for questions. Is that right? Thank you very much.
Cheers.
Yeah, if you have a question, you can use that microphone, and I can give you a microphone.
A few years ago, I worked in the MCJIT to do remote execution, and it was completely broken, and it's just slightly broken. The idea was exactly to cover the first topic there, but it was never used. So, you know, I don't think LLDB using JIT for the kind of expression is a hack. I think is a clever trick. But that can actually be, so if you could JIT your RenderScript core.
Are you looking at here?
Yeah. Yeah.
Yeah.
So if you could, because debugging on the GPU is very hard. You don't have breakpoints or whatever. So one thing you can do is you get your core, your kernel, right? And you say, well, set a breakpoint here. It means you compile, you JIT all the way until there, and then you stop, and you just compile that part, and you fire the JITted into the GPU, and it's going to come back because it ended for it, and then you get the result. You can read memory, you can see what happened, and then you compile the rest, and you continue, and that's how you set a breakpoint on the GPU. That's and then the remote execution with the JIT is the clever trick, because then you can use these things to set as many breakpoints as you want, because otherwise you can stop the core.
And yeah, because of this, also we can inject analysis information and hooks. So we can basically insert calls before the user expression to actually tell the GPU to do something else.
Yeah.
So I think this kind of flexibility is something that's really important to have in LLDB. And you know, it's under review upstream. I think it's probably going to go in eventually. But it's given us real great power to fix these really serious problems. And no one wants a seg fault when you call a function that's fine. You're going to think your function is doing something wrong.
Yeah.
And that's unacceptable behavior. And because of the limitations of having an intermediate representation that isn't purely portable, like for example, Spear V has been designed to be portable, but that didn't exist at the time RenderScript was specified. So we do have these challenges, and I think, yeah, as you say, that's a really powerful mechanism of doing it.
Exactly. Yeah.
Yes.
You mentioned that at some point software watch points. So can you determine the thread that triggered the software watch point in your current implementation? Or just you can say that, yes, someone changed that, but you don't know who?
Well, Ewan's the best person to talk about this, so I'll hand you over to him.
Yeah, so you have just the value you're expecting inside the atom, and then you can compare it to these values here. So you still have to hit the breakpoint every time, so it's a bit slower. But what was the question specifically?
So I know that, yeah, this is basically running instrumented code, and it's a lot slower. But the idea is, can you say, I'm running this code on all threads, or how can you say that the current thread that made the check and that reported the breakpoint is the one that actually changed the value of that memory location?
Well, the thread ID we're just interested in is the values from this memory location. So if, say, the thread in the LLDB is thread 1, 2, 3, 4, it doesn't matter. What just matters is the thread that has these values. So they don't have any corresponding relation to the thread IDs actually living in the LLDB.
Also, I think that's something that's unsolvable in the general case, though, isn't it? You know, if something modifies memory, the OS is going to give your debugger a callback saying memory was modified, but you don't have the information that says who in the world. It could have been a root process that's reading some raw memory. It's an unsolvable problem. So that's one of the real challenges with making this really smooth in a debugger is being able to tell what happened in the past. So you can either capture all state forever in a ring buffer, or you just have to accept that sometimes we're never going to be able to do that. Yeah. Yeah.
No, but for hardware watch points, you have, at least for x86, you have support from the operating system. So when someone modifies a value, you know exactly which thread and at which location it did that. And just saying is, does your system expand that to software watch points, or?
Not at this point. That would be a really good thing to add, I think. Yeah.
Yeah.
But that's a really good question. I think it's something that's really difficult to do in the general case.
Do we speaking about real memory breakpoints or batch points, or are they just breakpoints with conditional thread ID?
Yeah. Yeah, it's just a breakpoint of a conditional thread ID for. So you wrap up that thread ID, and then we just comparing the current breakpoint against that expected value.
All right, I think we're out of time. There will be hanging around for a while, so talk to them offline.
Yeah, come
if you
talk
have
to
more
us if you're
questions.
interested.
Okay, let's thank the speaker one more time. Thanks, guys.